Okay. Okay, perfect. Yeah, so it's super excited to give this presentation here on Uhepp at PyHEP2022. And as you already mentioned, the title of this talk is Sharing Plots in a Self-Contained Format. And throughout this talk, you will learn what this actually means and why this is advantageous. But first, I dive into the topic. Let's first point you to a couple of things. So the notebook is linked on the agenda. It's binderized. You can run it yourself if you like. I've included a couple of links to the actual Python package and to the documentation, the repository, and so on. And I will just go through this notebook. I will talk a lot what is actually going on in the background, but there's also text in the notebook itself. During this talk, you're not actually supposed to read all the comments, but I put them there for you to go through this notebook offline at your own pace if you want. So during the talk, you can just look at the code that's actually executed and what the output of the code is. So the talk is about Uhepp. This is primarily a Python package, but it's also a format specification and in part also an online service. And it's all about sharing histograms. So traditionally, histograms are stored in root files. This is very useful because we have the full information available. We have all the bins. We have the histogram split by a physics process or even by Monte Carlo sample. And we have, as I said, the full set of information. However, when we want to visualize this, when we want to look at the distributions and want to derive some insight or share this with collaborators, we need custom plotting scripts that take the raw histograms to graphics format like a PDF or PNG. And with this, we destroy a lot of information. We cannot read off numbers anymore. We cannot rebin easily. We cannot change the stacking or the composition of the stacks. So we lose a lot of information. And the difficulty with storing it in plain root files is that the plotting script and the root files get out of sync. You might impose a very specific naming structure. And once you change your plotting script, you need to make sure that all old root files still work with these plotting scripts. So this is rather challenging, and I propose a different strategy to tackle this issue. The solution is this Uhepp storage format. You can store it in JSON or YAML, and it combines the raw data, the raw histograms, with all the display settings on how to build the stacks, how to rebin, how to color, how to label, and everything. And with this, we can apply non-destructive changes later just to change the visual appearance, but still retain all the numeric values. And in this talk, we will just build a very simple histogram from toy data. And in the end, I will also talk a little bit about how to share this. So let's get started with a couple of imports. And I've prepared just one file. It's called toydata.root. And you will see in a second what's in it. So there's one histogram for signal, one signal for data, one histogram for data, and one histogram for background. So this is a typical setting. We have generated Monte Carlo distributions in signal and in background, and we want to compare this to measured data. And I read this with uproot, so we can look at the actual numeric values. So the raw data histogram has these numbers. I think the highest bin is 55. And if we look at the shape, you see that this contains 42 values. This is because I include under and overflow, and in Uhepp, usually you always have under and overflow bins. So going one step further, I also retrieved the statistical uncertainties from the root file and did what's called a yield object. This is basically just a combination of yield and statistical uncertainty. It can also store systematic uncertainties, but I will not talk about this in this talk. And I do the same with background and with data. And finally, I also retrieve the bin edges from this file. Maybe we can also look at the bin edges for a second. You see it goes from 0 to 200. And just to give you an impression of what these histograms look like, I have a couple of lines of plain Matplotlib. I draw them as steps without any stacking or anything. But you see in blue, we have a data distribution, we have an expected background distribution, and in green, an expected signal distribution. And it goes from 200 to from 0 to 200 with 40 bins plus under and overflow bins. So this was nothing new. So now let's move to the Uhepp package. Bin edges is 41 because we have 40 bins. And it all starts with a Uhepp hist object that takes the variable on the x-axis. It's called m because we're showing a mass distribution, and the bin edges. So that's that. And since this is supposed to be a self-contained format, we combine the raw numeric values in this yields dictionary that just maps internal names to yield objects. And later we combine this with the visual settings. So let's just store the raw yield objects here and move on to these visual settings. And in Uhepp, there's the concept of a stack and a stack item. So usually you want to have background and signal stacked on top of each other in the histogram, and then overlaid, we want to have measured data points as a separate stack, which is one item. So we generate a stack item for the background, and here we can refer to it again with these internal names that we stored in these dictionaries. And the same thing for signal. So here we could even change the splitting of histograms and combine multiple into single entries. And finally, we combine the background stack item and the signal stack item into one combined stack object and append it to the stacks in our histogram. I do the same with data. Only change here is that we specify this is supposed to be data points and not as a field histogram. And I go on and set a couple of other settings, like the variable name, that this is actually a mass and not just a simple m, the unit, a default name, and then an author name. And then there's a handy method called render, which just calls Matplotlib internally. And here you see we have the background and signal distributions overlaid and the data points on top of it. And you get a lot of additional features. So it automatically added the unit here at the x-axis, and also at the y-axis. You get uncertainty bands and uncertainty bars and so on. And we can also, since we have all the numerical values already, we can add a ratio plot here at the bottom in just a couple of lines. And now we can perform these non-destructive changes. So the bidding might be a little bit fine. This is perfect if we want to have the full information, but for visualization, we might want to rebin this. And here we can use the original bin edges, just sample every fourth bin, save this in another variable called coarser bin, and set the rebin edges property to this coarser rebin property. And now you see it's rebinned in a much coarser way. And we can save this as a PDF file. This is what one usually does to share it with collaborators or put it in publications. But the real advantage of Uhepp is that you can also save it in a JSON or YAML format. There's a method called toJSON. And with this, we save all the information that we set in this object to the JSON file. And we can load it again in a new session, or collaborators could load it in a new session with Uhepp from JSON, and then call render again, and you see we have exactly the same plot again. And we can even go beyond just saving files locally. There's also an online service. Unfortunately, this particular service, uhepp.org, is only available at the moment for Atlas members. But the code of this hub is also freely available, so you can host your own hub service at your own institute, for example, and then push these histograms to the remote service and look at them, inspect them visually in a preview, change the composition in the browser, and then, for example, send this link to collaborators. You can test this yourself if you want after the talk. And another real advantage of this online service would be that we can get this universally unique ID that we generated just by pushing it to the remote service and pull it again in a new session and restore exactly the same distribution again. And here we can make use of the raw information. So maybe now we decide, okay, the binning is a little bit too coarse. Maybe take the original bin edges and just sample every second bin and set this to this rebin property. Maybe also we want to change the colors. So here, change the colors, and we have finer bins and different color settings. There are more features like the semantic uncertainties that I didn't talk about, optional metadata. You can also superimpose graphs. There's a command line interface and so on. And I'm happy to answer questions. Thanks.
Okay, thanks very much. That was excellent. We have just enough time for maybe 1 or 2 questions. So let's go to Slido. Okay, so we have some questions coming in fast and furious, so I'll just take them in the order they showed up. So Michael wants to know, is there a way to convert from hist or th1?
There's a way to convert from th1. Initially, if you go to the GitLab or GitHub repository and go back in history, I had this set up for th1, but thought for this binarization, it might be easier to show it in with uproot. So if you go back in the history, you have an example where you convert root th1 directly to histograms.
Yeah, I'll also mention that while Frank has this nice binderized repo for us, the documentation is also pretty good and extensive, so people should check that out as well. We have another question, which is, can you do finer binning, or is the data is lost by then? Does the hist object have all the data?
The hist object has all the data. So maybe if I just go back to this example and delete the sampling, just take the original bin edges and set this to rebin edges. We could also set it to none. And then you have the original superfine binning again. Of course, there are assumptions like it assumes that everything is statistically independent, but usually these assumptions are well motivated.
Okay, so and then we have one final question from Jonas. Are you aware? Okay, so I can already answer this, which is that Frank is very well aware of them. But Jonas wants to know, is Frank basically aware of the scikit-hep efforts and compatibility, and maybe even using them as a backend would be great. So I'll let Frank respond to that, but I know that he's already quite well aware of them.
Yes, so I'm aware of them. I think there's not super much of compatibility. There are some interfaces for Uhepp with different frameworks to import data or to export it. But I'm not sure if there's something with his UHI and MLHEP. I'm not sure about this.
Okay, so that was an excellent